morning, everyone. First, I want to thank very much the organizer for inviting me here. It's first time in South Africa, and the conference sounds super exciting. The place is very, very beautiful. So my talk is on, well, the title of the talk is Molecular Simulation for Material Optimization. But in reality, I was invited because I'm the chair of a consortium in the UK that bring together people working in this field. So I will spend most of my time in discussing what the CCP5, which is this consortium chairing, does for the community, so that you might have some ideas about how we can collaborate and work together. And then if I have time, a little bit about my science. So first I want to introduce myself. So as my name probably says, I'm actually Italian. I was born in Italy in a beautiful place here close to the coast. But after my PhD, I moved to Germany. And then I am now, since 2009, academic at the University of Manchester. So here is Manchester, is a city in the north of England. Here is London. And our university is one of the, it probably is the largest actually in the UK in terms of number of undergraduates, and is what we call a city university. So we have a very large campus, which is very close to the city center. The campus has, this building typical of English universities, but also very large new ones. This is, for example, the engineering building that has just been opened this August. The city itself is, I think, very nice, despite the terrible weather, to be honest, and is a mixture of very modernist skyscrapers and more traditional industrial, typical north of England city. So this, of course, the city is very famous for a football club, and here I bring only the Manchester United logo because my son otherwise would kill me. But there is another one which I will not mention. All right, so the university is very linked with the city itself. In terms of our historic connection with HBC, of course, Alan Turing was one of the academics in the Department of Computer Science, which is now one of the world's leading department on computer science. But the city is also famous for the Industrial Revolution that happened in the 19th century, mainly in Manchester, where basically machinery has been put into the production of cottons mainly. And out of this industrial revolution, there has been basically the university really started. So I'm in the chemical engineering department, and to the undergraduates, we say that we are the birthplace of chemical engineering, which probably is true because of the industrial revolution. A lot of engineers, so basically the subject, the topic of engineering became a scientific topic, and one of the former most notable alumni of the university is James Preston Joule. But the Industrial Revolution also split into social changes and revolution. So Manchester is linked to worker rights and unions birthplace, I would say, and also women rights. So Emily Pancras, which is the person that started the suffragette movement for women rights, was. Okay, so I'm from Manchester, but I have been elected chair of this consortium, which is called CCP5 in 2021. So the consortium started more than 40 years ago in the UK. And the idea was to bring and actually build a community around a topic, which was molecular simulation. At that time was just starting around the world. The CCP stands for Collaborative Computational Project. There was a call from the EPSRC, which is our funding agency, for creating this project. And the number 5 was because this was the 5th project among the various other ones. As I guess is the audience here, this CCP project encompasses any type of science that is related to computation. So there are CCPs on biosimulation now, but at that time was astrophysics, plasma physics, engineering, etc. We are, I'm told, the only one that survived since the first call. And as I said, now I am the chair. So the consortium, each consortium is based around a specific topic, and for us is molecular simulation. The idea was to build a community that at that time didn't exist, and the field of molecular simulation, which is basically using computer to model chemical system, looking only at atomistic level, so forgetting about the so encompassing the electronic structure of the atoms in some kind of what I see there, in some kind of implicit way within the model. Just started in the 80s because the foundations, the physical foundation, were laid out a few years before, and the computers, of course, started to become more and more powerful, so they allowed this type of simulation to happen. So the area of modeling the consortium covers is from atomistic modeling to mesoscale modeling. So basically, we are just above the quantum chemist and just below the engineering type of simulation where you use continuum mechanics or continuum dynamics. So what the consortium does has mainly two, since the beginning, the INSEP had mainly two aim. The first was to build a community that didn't exist at that time, and this was through support of various networking activities and training as well. And the second one was to partner with software engineers to build the software to allow people to run the simulation. At that time, there were no software well structured and benchmarked to run this type of simulation. Myself, as a PhD student in Italy at that time, I remember contacting the people from the CCP5 to get their first molecular dynamics code. So if you're interested in see what the CCP5 does, we have a website you can join, and is for free. So with this collaboration with the software engineers, over the years, they developed a very large number of different codes that can do different type of simulation. So the first one that started in the 90s, probably, but a proper version was, I think, beginning of 2000, is DL Poly. DL stands for Daresbury Laboratory. Daresbury is a little city near Manchester, and where all these software engineers have been, where they are. And now there is also a very large HPC still in the north of England. This DL Poly is a code that does molecular dynamics simulation. I will explain very quickly, if I have the time, what molecular dynamics does. But I would say this was the first software available to the community that was well benchmarked, and it was free. So all these software are free. You can just you might have to register to the CCP5, but you can download the source code. Then attached to the DL Poly, there were a few other ancillary programs, let's say, that helps you to basically create the input file for DL Poly. And then more recently, we also have a DL Monte, which is a multi-purpose Monte Carlo simulation software. And then also through industrial support, we developed DL Meso, which is a mesoscopic simulation tool. Again, if I have time, I can explain a bit better what it means, but basically can run, for those of you that know what I'm talking about, can run dissipative particle dynamics and also lattice Boltzmann. And then we have also a Python interface type of program called ChemShell that allows you to basically interface two different codes, one that does the electronic structure calculation and with the molecular dynamics code to perform what we call QMMM calculation. So all this code are part of what we call the CP5 program library. Again, you can have a look at what these various codes and how to access and have them from our website. As I was saying, at that time, there was no community around molecular modeling. The tool was really, so the whole idea was really new, started mainly for protein, but then spin out in many other fields. So the idea was, okay, let's provide the software developed by scientists that know how to develop the software in collaboration with academics, that they can therefore ask the software developers to include into the software the various features that they want to do, depending on what they want to simulate. But another big part is training. So we have an annual summer school that we have been running from 1988. Again, I've been told this is the oldest summer school, at least in Europe, on molecular simulation. This school is a residential school. Anyone can apply from all over the world. We have a very large international group of students applying, usually targeting PhD students, but we also have postdoc, and also people from industry. Is a residential school, as I said, around 10 days in total. Is organized by different university across the UK. We also have a pre-course programming for those that are interested around for 3 days. I think we teach now Python, C, and I think I push for Fortran still, because that's what I use mainly. And then we have 5 days where we teach the students the fundamentals of molecular simulations, statistical mechanics, molecular dynamics in Monte Carlo. And then we have 3 days of advanced courses. The student can choose between 4 different topics: biosimulation, first principle, so quantum mechanics, mesoscopic simulation, so DPD and lattice Boltzmann, and also data-driven force field. We have also shorter training activities that we can run also upon request, which are a bit about how to use the software that we have developed. So it's more for users, but also what we call hack days. So for those that actually want to enter into the code and try to hack it. And again, if people are interested, we can organize here, is that around the UK, but we have discussion with Happy about seeing if there is interest here as well to have this kind of training. Again, all the training activities are on our website. So since I became chair, I slightly, my aim was to expand the core community around the CCP5 to experimentalists and data scientists. Since the 1980, molecular modeling has changed, so has become a more and more mature techniques. And now it's a very mature field with very reliable software available, very large HPC that we can use to run calculations and basically calculate any type of properties we are interested of, material chemistry, biophysics, etc. So the idea was to expand to experimentalists and data scientists with a big aim to develop this laboratory for the future, where basically molecular modeling is an integral part of the process to develop new material, new drugs, etc. So the idea was therefore to create a network with the different partners to help basically the integration of material modeling with the data science and experiment. So, and that's where the CCP5++ comes about, because we want to engage with experimentalists and data scientists. So we have been funded, and this is the list of partners for the network. Here you can see your institution. I don't know how to pronounce it, to be honest, but and then there are other international partners such as SICAM, which is basically CP5 version at the European level, and one of the organizations from the US as well. We also have support from companies. NVIDIA is one of them, and IBM, and also a few other companies that are consumer companies or that are interested in using the techniques. Then we have partner national institutes. I just want to highlight, you definitely don't know what they are, but basically this Alan Turing Institute is the National Institute for Data Science that I think was established just a few years ago. And the Royce Institute is instead is a large institute that is based in Manchester, where people can access any kind of characterization techniques for material characterization. Then, of course, the CCPs, as I said, CCPs is a group of consortia. And the idea is to have collaboration across CCPs. So, for example, we have strong collaboration with the CCP BioSim, which is the consortium that focuses on modeling of proteins, but also, for example, for the NQ, which is the neutron scattering one. The CCP9 is quantum mechanics. But we also work in collaboration with the consortia that are associated to the HPC in the UK. And the MCC is the one for materials modeling, and the UK CAMS is instead the one for mesoscopic modeling. So again, the idea of this consortia, both for the CCPs as well as for the HPCs, to bring people together for the HPC that use similar codes to optimize the code for the various architecture that, depending on what architecture we have, we have available, and the CCPs instead is more focused on the science. So again, this is just a list of external partners. So what do we sponsor? So the network sponsor a variety of different networking and training. So of course, conferences. I want to say I'm not going to start to. All right. So as I said, the vision of the net is to create this new lab for the future. The idea is really to take molecular modeling as an integral part of the process that you use either to, of course, solve fundamental physics problems, but also for material discovery, and also, we believe, very relevant for industry, so for products manufacturing and formulation and process optimization. Now, that's not that easy to do. It's much easier to write in a grant and actually do it. So we kind of try to focus on what actually is needed in order to achieve that. Well, one thing that's also the reason that's why I'm here is to increase awareness of power of molecular modeling in many different fields now of science and biophysics. One very important problem when you talk with industry is to be able to translate an industrial problem into a problem that can be solved with molecular simulations. Then, of course, the usual problem of language barrier between communities. And one thing that we have been very interested in, especially in Europe, is to engage with small and medium enterprises, because they might not have access to HPC or the type of skills, quite advanced skills that you need in order to use this type of software. So if I have time, I'll just go a bit in details about what this CCP5 is, what molecular modeling is. So when you try to model a chemical system, you can decide to model it at different degrees of details. So you probably all know atoms are surrounded by electrons. So if you want to model a system, you can actually take into account all the electronic structure of each of the atoms, and you can perform what are called quantum chemical calculation or electronic structure calculation. In order to do that, you have to solve a very complicated equation, which is called the Schrödinger equation. So because it's so computationally demanding, basically, you can model a system at very, very high details, but the number of atoms you can model is reduced to around a few hundred. And the time scale of your simulation is also very limited, would say a few picoseconds. So this is a time scale which is relevant for reactions, but if you are after other type of properties, so more thermodynamic properties, for example, this type of number of atoms and length scale is not enough. So one way, that is what happens really in the 80s when they start to develop the fundamentals physics for this jump, basically, and then later on the software, is that there is a way to take into account in a kind of implicit way the effect of all the electrons around the nucleus of the atom. And basically, it is possible to describe your system rather than using quantum mechanics, using just standard classical mechanics. So if you do in this way, the number of degrees of freedom of your model is massively reduced because it just depends on the number of atoms you want to include in your model. And then you treat each atom as a classical object, classical in the sense there is no quantum effect. So in this way, the equation you have to solve is just the Newton equation, F equal mass times A. If you do that, you can increase massively the number of atoms you can include in your model up to millions, and you can run the simulation for microseconds. So human time is probably weeks, but you can see the system evolving over time for microseconds. Then you can do this kind of coarse graining that you have done from quantum chemistry to atomistic model even further and start to lump and describe several atoms as a single classical object. You do this, it's called coarse graining model. The advantage of moving from here to here is that you have even less number of particles, and therefore you can run larger systems for much longer time. And you can do this up to a certain point. A certain point, the number of atoms you want to collect in a single particle becomes so big that you can't really treat it as a classical object anymore. So assuming that it just moved through classical Newton equation, and you basically you cross over to the continuum modeling, like finite element, where your smallest degrees of freedom is actually a unit of volume. So the equation you solve is the Newton equation, force equal mass time acceleration. You have to integrate this equation over all the degrees of freedom you have. And that means you, first of all, so I'm not going into the details, but the mathematical formula that describes the force is very complicated. It is a multi-parameter functional form, a derivable one. So basically, this equation cannot be solved analytically, it has to be solved numerically. And then at the end of, and that was the big challenges in the 90s and early 2000s to find algorithms that can solve this very quickly. At the end of a simulation for a molecular dynamics, okay, that's what I'm talking about. Monte Carlo is slightly different. You end up with a trajectory that contains all the position of your atom over time. So you get kind of a movie and you can follow how the atoms move either in steady state, so you don't apply any bias, or when you apply bias, and this bias could be a flow, could be pressure gradient, concentration gradient, electric field, or whatever. The method is deterministic in the sense that we don't have any statistic variable into it. Okay, so if I have the time, 5 minutes. I will go very quick just to showcase something that molecular modeling can do. These examples are taken from my group, but are so wide and different topics that really represents, I would say, the whole community. I decided to focus on 3 examples that come from collaboration with companies. So the first one is a collaboration I had for many years with Unilever. Unilever is a company that produces formulated products such as shampoos, conditioner, laundry products, but also food. So all these products are basically the same thing, are colloidal systems. So you have an aqueous phase in which you dissolve large molecules that are water-like and water-dislike. So they are composed by 2 different chemistry. And when you add enough of these molecules start to assemble in massive large objects that are called micelles. This is the basic way in which soap works. So this micelle, you have to imagine some kind of spherical object in which the core is hydrophobic, so can grab dirt, which is usually oil stuff, and the external part is watery. So this large object, despite being large, they can be solvated in water. So the soap look like an homogeneous fluid, like the soap we use to wash our hands. But in reality, if you zoom in, it's formed by this water molecule. So the water liquid inside, you have this large micelle. Now, this micelle can be spherical, but can also have different shape. Depending on the shape, you end up with the liquid detergent liquid, for example, which has different viscosity. And as a consumer, we expect certain viscosity for different type of detergent. So for example, we expect conditioner to be more viscous than shampoo. Now, if the company wants to change slightly the formulation, it's basically impossible for them to predict how much is going to be the viscosity of the final detergent. And this is a massive problem for them, also for the environment, because they have, every time they have to come up with a different formulation, they have to clean up all the batches and stuff. So we use a mesoscopic model, this DPT particle dynamics, and one of the CCP5 code, the LMESO, to develop a molecular model for the surfactant system. And what we did here, we built a phase diagram using a bit of machine learning as well. So we told them basically the shape of these micelles. These are like spherical. These are, you see, a bit elongated one. These are very long one as a function of concentration of the surfactant and also salt, which is another very big important component of all these formulated products. And then we also come up with an idea about how to calculate the viscosity of this fluid so that they don't actually have to go to the lab and test first. They can use DPD, which is quite efficient way to run simulation to screen various surfactant or concentration of salt, or for example, they want to add a new fragrance or a new dye or whatever, and then try to figure it out what's the best surfactant or the best qualitative, okay, ratio or concentration in order to have to be in the viscosity range that they would like. The second example is on a completely different topic, is polymer composite. I work a lot with Continental, which is a company that makes tires. So these tires are polymer elastomers, so polymers, polymer matrix, polyisoprene. And inside you have a lot of different components. But one thing they have to add are solid fillers. For the cheap tires for trucks, these solid fillers are carbon black, for example. So this addition of fillers is added to make processability easier. So they reduce the glass transition, but also to improve mechanical properties of the tire itself. The problem is that when you add this carbon black into the polymer matrix, so what they want is to have it disperse everywhere, to have an homogeneous fluid, but in reality, this particle tends to aggregate. So again, they wanted, without going to the lab, to try to figure it out, what is the surface chemistry that is the best to have a good dispersion of these fillers. So again, working with them for several years, we have been able to, end up with a software that allows them to create ideal surfaces that represent statistically the experimental sample they have, and calculate how much is the adhesion forces between the polymer and that surface. And this gives them an indication about how likely is this filler to be dispersed, because that will depend if the filler prefers to interact with the polymer or interact with itself. Just to mention, we work with IBM as well to develop neural network with them. Again, IBM, we have the UK, EU brand very close to Manchester, and that's it. So the HPC in the UK, we have tier 1, tier 2, and tier 3 HPC facility. Archery is the national one. We have a lot of regional ones as well, which are ideal for people running our simulation because they don't scale that well in this large cluster. And we also are lucky that university has very large HPC as well. And finally, I want to thank everybody, of course, and NICIS as well. And thank you very much for your attention.
So we just have time for maybe 2 quick questions.
Hello, thanks for a lovely presentation. First question, it's a bit general.
Yeah.
Since it's the first time in South Africa, how's the weather?
Weather is not great. You get used to it.
All right. On your annual summer school, is it open for every university in South Africa?
Is open to anyone. Anyone can apply. We are massively oversubscribed because we have practical sessions as well in the afternoon. So we are bounded to the number of HPC, space we have in the computer cluster of the university that host us. But over the years, we have run, so basically we really created a very good way of teaching molecular modeling to postgrads. So we have been running this summer school also around the world. So I think 2 years ago, they were in sorry, in Chile, I think it was. And we were asked to go to Malaysia, and then COVID started. Unfortunately, we couldn't go. So the idea, I guess, talking with Patricia Hall, was that perhaps if there is interest here, we could help you in organizing something similar here. But anyone can apply from all over the world. We have people from India, people from any type of any country. It's open.
Thank you very much for the presentation. I enjoyed seeing the collaborations with Unilever and Continental. Do you find it easier to get people excited about the output of their work when you can relate it to everyday real world items like shampoo and conditioner and car tires?
Mm-hmm. So yeah, that was, I guess, the aim here. And this it depends on the audience, and also depends on the students. Some students are very like to see the application in real life. I have a great PhD student that went to work in BSF, and that's the type of project she wanted. But there are others that instead prefer more kind of blue sky research. But my aim was to show that the field is very mature and can really, with the right question, you can really use and integrate into the process that normally industry have to, when they develop the product from the lab to the manufacturing.
All right, thank you very much. Um, Nikis, I think that's the correct way to pronounce it. And the CHBC would like to thank you very much and for your wonderful talk and traveling all the way from Manchester.
Okay,
I've been to Manchester and didn't like it. It rained all through. So
Thank you very much.